So good morning, and do you hear some noise from the outside, from my mic?
No,
'Cause
no, it
I
doesn't.
think
Mhm.
other families are also taking their vacation next to our apartment. So
No, no, it's all fine. Everything
yeah,
is clear.
but yeah, maybe if it is maybe disturbing, then I will just close the window. And yeah, and also one problem is I think I can't find my pen, like S Pen for my Galaxy Tab. So maybe we
Hmm.
should really do the mental math. And last meeting, I suggest that we should also start training for calculus calculation.
Hmm.
And have you take a look at this?
I looked at the source material. I haven't gone through the exercises yet,
Mhm.
but I've looked at it. It looks quite reasonable in the approach, and maybe because again Tanvir is joining the meeting today, I
Mhm,
guess
mhm,
maybe we
mhm,
discuss it a bit and see how we approach it and what the like purpose of which specific cases maybe.
mhm. Yeah, so maybe I'll explain about this Nota game, and then I mean after Tom Fair join us, and then maybe we have a like take a simple look, and yeah, and also we have just one exercise to end this third note of
Hmm.
that
Hmm.
theory. Hmm. So we have to show. So the left side there's exercise under the Korean letter, and it says F, which is equivalence classes of X, becomes a partition of X.
Hmm.
And we also have to, so in this case, we have an equivalence class. It becomes a partition of X. That's one direction. And the other direction is like we have a set X and we get the partition of X, then we get relation as an equivalence relation. Oh, I see. Hello, Tanfi? Can you hear me?
Hi,
Yeah.
yeah, what's
Hi.
up?
So
Hey,
do, do you feel okay now?
yeah, I'm feeling better.
Yeah, it's been a while, I think maybe around like 2 months
Yeah,
after
actually,
we, yeah.
pretty well.
So yeah, how have you been? I think you also joined another study in our enjoying math community.
Oh,
Like,
yeah, we are doing geometric measure theory, so it is kind of off for 2 or 3 weeks also. But
hmm
we have learned some things like, formalization of
hmm
probability and then the concept of measures in the normal sense. But
hmm
yeah, there are still a lot of stuff to come in the coming days.
yeah,
So, how was your semester and everything?
yeah.
How was the
So
exams?
so exam was, I think, okay. Okay, it was okay. And like higher semester students said like our second semester is most like dense and tough semester. But I think we gone through it well. And yeah, actually I'm in vacation now, so I mean, not here,
Oh,
but
okay.
somewhere in Germany, like North Germany, called the Lüneburg, like north
Oh,
of the
okay.
Germany, and yeah. So I I hope we can finish our meeting around like 9:45. So 1.5 hours will be okay. And yeah, for me, everything is good. And also, Philip, how was your?
Yeah, I would say the same. Hopefully, the semester went quite well. Hopefully, everything is okay with the exams, and since we're now in holiday, we get some time to switch the atmosphere, and then maybe yeah, be ready for the next semester as well.
Oh, okay,
Mhm.
that's good. Yeah, I was also a little bit busy give quite some interviews with some
Mm.
professors actually here and there. And yeah, recently I just finished working on a paper
Mhm.
on
Yeah, that's
the recording theory. So yeah, just submitted it on archive maybe yesterday and will submit on a journal maybe this week.
mhm. Yeah, maybe one day
Okay, yeah.
yeah, you can just introduce us or about your paper, even though we don't have much knowledge about that, but maybe we can get the impression of how like
Yeah, yeah, definitely
graduate
it will be fun.
mathematics like looks like. And we are currently on at the last chapter of our note three, which is also the end of the set theory. So today we will I hope we will go through the exercise on our left side. By the way, can you see the screen sharing? Like,
Yeah, yeah, I can see
maybe
both of
something
them.
like
Yeah,
that.
the same for me.
Mhm. So above the conversely, there's exercise that equivalent class of X becomes a partition of X, and the other way, which is we have a partition, and then the relation between the elements in X goes I don't know how to precisely describe the argument, but yeah, then we get a we have a equivalence relation. So I hope today we go through this exercise together. I mean, not full formal writing of this proof, but at least the logical deduction and yeah, logical idea of this proof. And then the other way is on your right side, there's a note. Maybe I should. Mhm. So in our community, Professor Cho and Professor really emphasize the importance of doing and drilling the basic calculation of matrix calculation, simple matrix calculation, and also calculus, single variable calculus. But yeah, really simple and yeah, basic stuff, but really made it concrete to the ability. So I attached the first note. I think it composed with like 12 12 notes with single variable calculation. And yeah, I sent our channel for the first note. First note is about limits. Yeah, limits of sequence and functions. And I hope we also add this material to on our studying. So for
Yeah,
this,
that will be great actually. I think we should solve a lot of exercises.
yeah, so maybe it reminds your high school, yeah, period. And for this one, I hope we solve this with hand first before our meeting. And then if when we do our Monday meeting, we going through this, just ask the, for example, we just do we just solve the problems one by one, but just thinking out at like yeah, just like mental math, but explaining the process of the calculation. For example, like I'm not sure like what's the best way to train this in our meeting, but that's how the other Korean studies in our channel do. So I hope we also, yeah, maybe mimic that way, and yeah, I hope we all get the skills.
Did you hear from other groups how they approach it during meetings? Do they
Hmm.
discuss problem by problem, discussing the approach to the solution, or do they just practice separately and then?
So they practice separately, and when they do the meeting, they ask each other. For example, like Philip, please tell me the limits like infinite limits of 1 plus 3 over n to the power of 2n, then you have to tell the answer immediately, or you can just explain the process and then tell the answer. For example, in this A1 and sub question B, we have 1 plus 1 over n to the power of n is
Mhm.
exponential. So in this case, we have yeah, in this case, to the power of e to the power of 3,
It should be, yeah, 3 times 2.
yeah, 3 times 2. So yeah, it's really been a while, but yeah, we have this, and so we have 2 times e to the power of 3. Mm,
Yeah,
mm.
I got it.
So I hope we can start this from next meeting. I hope.
Mhm.
Mhm. So we have A, B, C in our first notes. So maybe we can just go through these problem sets once with our hands, and just before we start to discuss the Kidesu notes, I hope we go through this first.
Okay.
Mhm.
Is
And
it
and
clear?
also pretty much every time you will be giving out a new problem set, then
Yeah,
roughly every
yeah.
week we have. Mhm.
Yeah. So it starts with limits, but yeah, I think the most of the content will be the basic calculation of derivative and also integrals. And yeah. So I hope from next meeting we train this before our Kidesu like
Mhm.
session, and also even before starting our Kidesu session, we always ask each other, drilling the definitions and or sort of things. So, and maybe I want to ask Philip, what's the definition of equivalence relation?
Uh, yep.
Yeah.
So it's also sorry I haven't looked at it in like the last days.
Mhm. Okay, then what's the definition of relation?
Mm.
Yeah, maybe if you can't come up with the answer immediately, you can just give the question back to me.
Yeah, if you don't mind, maybe.
Yeah.
Yeah, thank you.
So the definition of relation was a subset of Cartesian products. So any subset of Cartesian products are relation. I mean Cartesian products of two sets. So subset of Cartesian products of two sets was relation. Please stop me if there's something unprecise, but yeah, that was the definition of relation I remember here. And equivalence relation fulfills the three criteria among the relations. So first, it should have reflexivity, which means it has the relation to itself. So x related to x. And second, we need symmetry, which means if we have x related to y, then we must have y related to x in our relation. And third, we need transitivity, which means if x related to y and y related to z, then we need also relation with x related to z. So if relation holds these three criteria, then we call that equivalence relation. Is that right? I mean,
To me, it sounds like you covered every point that is necessary
mhm.
for the definition.
So okay, so now I want to ask Tanfir, what was the definition of function?
Okay, so first of all, function is also a kind of relation
Mhm.
uh, where actually each of the elements from the first set is related to exactly one element on the second set, which we formally call domain and codomain. And another thing is no element of the second set is actually related with multiple times with the first set. So this is more of a, like a formal syncretic definition for all. Let's say we have sets A and B. So, for example, for all elements of A, there exists an element in B such that like the function of the elements in the first set equal to the element in the second set. It's just there are no multiple elements the second set which are related with the uh, single element in the first set. I'm not sure whether it was clear. Did it make sense?
Yeah,
To me, it was yeah. Uh,
yeah, maybe.
so again, maybe what we're I think checking ourselves is that what we say is a complete definition, and it's without any sort of we don't accidentally introduce some mistakes or some kind of bugs in between, right? That's roughly
Yeah,
two criteria that we're checking.
Mhm. Yeah, and also maybe Tanfir can ask Philip or me for some definitions, what we had, or yeah, maybe, or you can just choose between definition of injective function or like one-to-one function, on-to function, or definition of partition, or and you can pick Philip or me and just
Okay, and maybe just one sub question. So the further we go in with sessions, the question is: do we jump between any material previously covered, or do we try to sort of only cover the nearby material? So something we covered only recently
yeah,
for
it
the
depends.
definitions. Is it better, or do we mix it? So do we sometimes approach it from one side, and sometimes it's like from all the material that we studied previously, so we can.
Yeah, it depends on us. So.
yeah, maybe it will depend on the topic also. Maybe sometimes when we are going to study a topic, somehow it is related to the concept of Cartesian products, let's say. So we go back to the definition of Cartesian products, and then we start the topic again. So maybe that's how it will be a back and forth contextually.
Mhm.
Yeah. So,
I think basically so far the material we covered it forms a certain like a group on its own because it covers the material which is really closely related. And the next topic that we're going to have in Kidosu notes is about uh, introduction to analysis. So I think it starts as sort of new aspect of everything. So maybe that's roughly how we can organize our drilling ideas. That when we are within one section, we cover the material from that section and jump back and forth. But in the new section, maybe we try to um, not intermix too much of the material from previous sections, as to not to confuse and still to sort of reinforce what we understand about that specific section.
mhm,
But it's just like I guess so far. So maybe we'll
yeah.
practically understand it better later.
Mhm. But I think, from my opinion, like just all definition in this note is really basic and just like core thing in our at least our career and just in mathematics. So I think we at least we feel comfortable about all definitions in this note. I hope so.
Hmm.
So so if Samir feels hard to choose one of us, then I will choose Philip to explain the definition of one-to-one, also called injective function, and also surjective function.
Mhm. Well, for the case of injective, again, if we're speaking about the sets on sort of two sides, then we would say that for in the injective case, we would have at most one connection to the codomain set, and for the surjective case, we would have at least one connection to the codomain set. And then when we have both of the properties satisfied, we have a one-to-one relation between the both sets. And again, maybe with the case of injectivity with respect to what's not possible with injective relation is that we cannot have multiple elements uh, in the domain arrive to the same element in the codomain. And for the surjective case, we can have multiple elements from the domain arrive at the same element in the codomain. And also we should cover the full codomain.
Mhm.
Yeah, makes sense.
Yeah, could you describe at most one and at least one the description of like the usage of at most one and at least one? Because
Uh,
it was a bit ambiguous.
okay, so when I say at least one, I mean that uh, there is for every element in the domain uh, a connection to the well basic to the codomain, such that all elements in the domain have to at least relate to one. Uh, yeah, I'm getting a bit stuck myself.
So you
Is it for the injective definition?
Yeah, it is for the injective. Yeah.
Yeah, so technically for the injective definition, what happens is every element of domain is uniquely related with every elements in the core domain. So by unique, we mean that if any element from the domain is related with another element in the core domain, then there is not another element in the domain which is related with the same element in the core domain, right?
Yeah, I
So,
think basically you gave the explanation which clarifies it.
yeah.
and another thing is it's not necessary that all of the elements in the core domain is related with uh, some elements in that domain. I mean,
Mhm.
that's the criteria for subjectivity, I guess.
Mhm. So maybe what Philip want to use the term at least and at most was in terms of the codomain. So like every element in codomain has at least one pre-image, then we call that surjective or onto, and every element in codomain has at most one pre-image, then we call that injective. Maybe is
Yeah,
it the yeah, is that the context what you want to use the term of at least and at
Yeah,
most?
that's what I tried to the meanings I tried to assign. Yeah. Mhm.
Yeah, I mean like I mean it's not always easy to come up with that in Monday morning
Yep.
8 a.m. But I think it will help us to really get the idea and yeah. And I think there's one definition we also have to drill, which was the definition of partition. Maybe Tamfir, can you describe the definition of partition?
yeah, definitely. So a partition of a set is a collection of non-empty subsets such that every element of the original set belong to exactly one subset in that collection. So, and it also actually, let's say, follow some criteria. For example, let's say we have a set A and we have a collection of non-empty subsets of A. It could be anything, let's say U. So we call that U is a partition of A. For example, if the union of all of the subsets in that collection are equal to the original set A, and all of the subsets are distinct, like if we take an intersection, it will always be an empty set, and all of the subsets are non-empty.
Yeah.
Mhm.
I think that makes sense. So in our node, I think we
Yeah, it's broken into three parts. So
mm,
first of all, each subset is essentially non-empty. All of the subsets do not intersect, and collection of all the subsets makes for the full set.
yeah. So I think Tanfir exactly explained us with a more like soft way, I should say. Yeah. So that's the that was the definition of partition. And so we have to go through the exercise that equivalence classes becomes a partition of X. And are like for Tanfir, are you used to this correspondence between equivalence relation and partition?
Yeah. So,
Yeah.
for example, we know that equivalence class are defined by, like, let's say for any class A, so we have all of the elements in our original set. Okay, so it's a little bit hard to describe that, right? So if we have a equivalence class, let's say small b, for example, we have a class of b. So the elements of this class are all of these elements in the original set, such that those elements are those elements have a equivalence relation with b. Does it make sense? For example, our original set, let's say U. So if our class is B, so the elements of B is basically all of the elements in U, such that, let's say those are X, we are saying, so X is equivalent to related to B.
Mm-hmm.
So that's how we form a class.
Mm-hmm.
And then we have to show that actually all of these equivalence classes, like let's say I just said B, let's say B is a class, so maybe we have some other classes also. We have to show that their union actually forms our original set U. Right? I mean, am I being clear?
Yeah. Well, it's from just the definition, right? That we just
Yeah.
discussed before.
And I think this is quite obvious in a sense that, like, we know if any element belong to any class, so it cannot belong to another class, because by that sense, if it belongs to another class, then both of the class are same. So that's how we get the unique situation that every elements belong uniquely to any single class, not in multiple classes. And as every element from the original set belongs to like at least one of the classes, I mean exactly one of the classes. So of course, if we take the union of those classes, we will get the original set.
Mm-hmm.
Okay, yeah, please. Yeah, please
My
tell me.
my only question maybe for this exercise is how would you verbally formulate it? So given that F is a collection of all classes, then it is a partition, or how would you say that? Because we are supposed to go from one side in this exercise and from the opposite side in the next exercise. But which side are we talking about in this exercise? So how do you actually specify this problem? How do you sort of pronounce what the exercise is exactly? So we are trying to show that.
Maybe I could say.
Okay, yeah. So we have to show that like the collection of the equivalence class forms a partition.
Mhm, mhm,
So in that case, as we know from the definition of partition, that actually the collections, the elements of the collections has to be non-empty, which by default we know that every class are non-empty here. And secondly, we have to show that the union of the collection, like the union of those classes forms the original set. And thirdly, we have to show that the intersection of those classes are the null set,
Mhm.
right?
mhm. So in here, the only thing is that we have to sort of go through each of the conditions for what a from a definition of a partition, and that would be sufficient as the to
Yeah,
show that, right? Okay.
yeah.
Yeah, so
So,
for
yeah,
me,
yeah, go on.
it is clear and trivial to um, think about the intersection between equivalent classes are null set or empty set, and
Mhm.
union of all equivalent classes makes the
The whole set.
whole, yeah, whole set. So the second and third criteria, it feels quite clear to me, but the first one, non-empty set, um, like is it always guaranteed in this setting? That yeah, that's the point I feel not sure about. I mean, what is our argue?
But my guess is that if you say that just some element x which belongs to the set x, it has to go somewhere. So even if you define an equivalence class which doesn't contain anything else, it can fall into that class as well, right? So if there is some element in a set that is not equivalent to any other element, then it forms a separate group on its own. So essentially, you can pick every single element out of the set, and it will go into some class whether it has elements which are equivalent to it or not.
Mm,
I think it can also be make sense in a way that when we are actually defining the collection of subsets to form a, let's say, equivalence class.
mm-hmm.
Mhm.
So what we are doing is basically we are not taking those subsets from the collections from the power set of the set, right? Like we are taking those collection in a sense that we want to see like whether every element of the original set belong to somewhere. So that's how we form the collection. Because if we are taking the collection, let's say from the power set of the original set, so maybe the empty set would have come up in here because empty set is the element of the power set.
Mhm.
And also empty sets are also the collection of subsets of the original set. But in this case, we are taking the collection with this in mind that every element of the original set somehow belongs to one of the elements in our collection of subset. So that's how the empty set doesn't come up in here. I'm not sure whether it makes sense.
Yeah.
Mm. Was that the question you had, Bohyan, or you had a different aspect that you're not unsure about?
No, it's
Yeah.
more of like the question was, I guess, why it always has to be non-empty, right?
No, no. So my question was, how can we obviously show that the equivalent classes are non-implicit? And yeah, I think the explanation from Tamfir makes sense, but maybe the problem is I just yeah.
So you're
Not
asking for a
just
case
clicking.
when we have X as the empty set itself, for example, X is an empty set. What happens then? Is that a kind of special case that you're considering?
I mean, the argument that so we have to also show that all equivalence classes of X is not empty set. So in the middle of our note, we have exercise and we define F as a set of equivalence classes. So we pick X from the large X and all elements from large X we make equivalence classes and the set of these equivalence classes form a partition of large X. So my wondering is the like is the just the equivalence equivalence classes makes the property of non-empty set, or is there specific something else make this
I'm just wondering if we can, for example, if you draw, just as an example, like a circle which to represent a set, then a partition can be drawn as either like many lines crossing this circle, right? And essentially, if you draw a line such that it only borders the side of a circle and doesn't contain any of the elements of the circle, then it's not really a partition of that circle. So when you say it is a partition, it's essentially breaking uh, into specific groups.
I mean, but we are taking equivalence classes and we have to show that these equivalence classes are fulfill the criteria of partition. So in I mean we are not starting from the partition, so I think we can't use
Uh,
that approach.
okay, so in that sense, I feel it might be related with the definition of the class. For example, if we think about the class X, so let's say this X is the empty set. So now, as this is the empty set, for example, so we have an empty class. So what does it mean? By definition of the class, so there has to be some element in our original set which is related with the empty set, but that is technically not possible. So that's how we don't create any empty class because
Mm,
actually there are no elements which are related with the empty set.
mhm. Uh,
Yes,
so then,
I think this explanation with respect to the empty set makes it clear that either there are some elements which such that X is related to Y, or there are no such elements, right?
Yeah, yeah.
so like by construction, we have all equivalence classes are non-empty.
Yes, that's what I.
Hmm.
Sorry, my camera is overheating the
Yeah,
phone again.
yeah, don't worry. Yeah. So yeah, so then the like non-empty criteria is just like
And
automatically.
another thing I want to mention is non-empty criteria comes from the reflexive property, by the way. I think because if you think about the class, let's say the small a,
Yeah, yeah.
so always every element are related with that.
Yeah, yeah, yeah. Now, yeah, I think, yeah, yeah. Now it's obvious. Now it clicked to me. Yeah, thank you.
So probably the reflexivity then is the key which you can explicitly show, right?
Yeah, yeah.
Mhm.
Mhm.
Every element is related with itself, so by default we don't get any
Mhm.
non-empty class.
Like, so one sub question is like equivalence classes are just so in this tilde r notation in our note means like defining the equivalence classes. The tilde r means equivalence relation, but what if we use just relation? Then these sets will be also non-empty. Use if we use the same definition, but just only change the equivalence relation to just relation?
Then I think the classes need not to be non-empty. I mean, it will depend on how we define the relation. Yes.
I think in sort of more casual terms, we can say that if there is an equivalence relation, then you know for sure that there is at least two elements are related with each other. There are at least two elements are equivalent to each other. Whereas with the general relation, you don't have that restriction. You don't need to have at least right. You can just empty set would still be okay, I guess.
Yeah, I hope so.
But I'm wondering, even if we use just general relation, so even we have an empty set as a like one pair of Cartesian product, then empty set itself will be the element of this set. So it might be non-empty, even we in the just general relation setting, or can you come up with one example that if we use the general relation, then we can have a just empty set for this definition if we just change this
Uh,
relation as
let's say let's say we have a set whose elements are one and two,
mhm,
and we define a relation R with the ordered pair one two only, just the ordered pair one two.
mhm,
Hmm.
Okay, so we have a relation, and the order pair one two means one is related to two, right? Not two is related to one.
Hmm.
mhm,
So if I take a class of, let's say, uh, two, let's say this is a class of two, which means, sorry, this is a class of one, which means all of the elements which are related with one. So I don't have any elements in this class because one is related with two, but two is not related with one.
mhm,
So this class is actually empty.
So
mm,
there exists a normal relation, but there doesn't exist an equivalence relation in such a case.
Yeah,
yeah,
that's what
yeah,
the reflexivity
yeah,
property actually guarantees that.
yeah. Now it makes sense. Yeah. So in this, yeah, okay. So it depends on really how we define the relation, and in that case, that we don't have a mapping, or yeah, yeah, mapping, then
Yeah,
it will be just relation. Hmm. Yeah,
yeah.
that was nice. Yeah. So so for now, I think for me it's comfortable with the one direction that we start from the equivalence classes, and yeah, and then maybe we can think about the other way. So we start from the partition of X. So in here, alpha is from index set, and I think this index set is construct for the construction of the partition, which is like the subset has index alpha to distinguish with the other subsets.
I think we during last time we discussed the idea that in this case, indices sound more like labels, so you can label a specific group which contains equivalent elements.
Mhm. So in this case, we have partitions, and if we pick two elements from the one subset, then um,
How is the equivalence class defined
mhm.
here?
So how could we start from here? So
Yeah, so
so
the
what?
equivalence relation here, like how do we define the equivalence relation here in this case?
Mhm. So we have to show that all elements, so like E alpha, we have to take a look at E alpha and their elements, and then like E alpha in there, we have to show that it has reflexivity, like all elements, like if we pick two elements from E alpha, then between two elements, the relation has I mean, even we do the Cartesian product of E alpha, like homogeneous Cartesian product of E alpha to make a relation. That's how we define a relation, and then we have to show that this relation fulfills reflexivity, symmetry, and transitivity. Like, is that the setting?
Yeah,
What
yeah.
we okay.
I think so. So essentially, we start with E alpha Cartesian product with E alpha. And essentially from there, we can see that we get all the possible properties. So we get all the required properties. So we get reflexivity.
Oh, sorry. What? How we get reflexivity?
If you get the Cartesian product and you basically pick the element. So we know from the definition itself that E alpha contains only the equivalent elements. So elements which are equivalent between themselves.
Why?
Because we started with the partition.
Mm-hmm.
And in this partition, E alpha contains elements which are equivalent between themselves, right?
I mean, why like partition implies the equivalence itself? I mean, that's what we have to show. So I think we cannot use that property like that directly, or maybe we can.
I
Maybe Tampi, you can. Um,
well, okay, so we are starting from the definition of partition, right?
Mhm.
So since the elements of the partitions, and if we take the union of that, we will get the original set by definition of partition. Okay, so therefore, let's say if we pick any element from the original set, it will belong to some element in the partition, right?
Yep. At least.
Because by the definition of partition, the elements of the partition actually, like the union of that, will give us the original set, which means every element in the original set belong to some element in the partition by default.
Mhm.
So now I can say, now it's just a redundant argument kind of. So let's say X is a element of any element in the partition, and I can write X twice, which means X is related to itself. I mean, hence we get the reflexive property. I mean, this is just what I'm trying to say.
Yeah, I for me it sounds like it's definitely there is no exception where it cannot have a reflexive property. At least it sounds like. Bohyan, do you have any kind of comment on?
yeah, I was just again confused what we are trying to show here. Um so I so in the second line in our second exercise, so define x related to y, and xy comes from the large set X. So mhm.
So technically speaking, by the when we say that like X is related to Y, what do we mean? X and Y belong to some element in the partition, right?
Mhm.
Uh, so we have to show that this is reflexive. So in terms of reflexive, X is related to X, and such that X and X belong to some element in the partition. And we know it by the definition of partition that X belong to some element in the partition, as the union of the partition gives us the ordinal set. I mean, the
I'm just
union of the elements of the partition.
I'm
Mhm.
just wondering if the problem is the question is more about how do you formulate it out and such that you don't make any kind of assumptions instead of only rely on the on the sort of properties you have, right? So if you were to write a formal proof, how would you approach that? That is the problem, right?
Yeah, actually, I was a bit confused of the like sentence if here because I thought that we defined the relation x y from large X, but yeah, I understand that we do the Cartesian product of large X, like homogeneous Cartesian product of large X, but and then we like narrow down our scope to the alpha set, and if we have like indexed set E alpha, then if we have xy in E alpha, which means like the pair in E alpha, then it goes to it forms a equivalence relation. So yeah, I was a bit confused of just like understanding precisely the setting, but yeah, now I get the idea. So what we have to do is just show that this relation has reflexivity, symmetry, and transitivity, right?
Yeah. Also, just a curious question. You also said homogeneous
Mhm.
something. Homogeneous what? Cartesian product.
Yeah, yeah. I mean like X Cartesian product X in this case.
Oh, okay, okay.
Yeah,
Because
yeah,
you were like, what is non-homogeneous Cartesian product?
yeah.
Okay, okay.
I mean like maybe this is a bit like out of the main context, but is it possible to make an equivalence relation doing non-homogeneous Cartesian products? For example, like A and B is a different set, and if you do a Cartesian product with A and B, that even in that case we can make an equivalence relation because like last week, maybe it was last week with Philip, we did the meeting and maybe in the YouTube video from Professor Cho, he slightly mentioned that it shouldn't be always the like homogeneous relation to make a equivalence relation, but we thought like if we have a different set A and B and we do the Cartesian product, then even it is like ambiguous to define what reflexivity means if we have like different sets. So
I think basically when we discussed last time was the idea that the definition specifically said that homogeneous relation would be totally accepted. So Cartesian product with the set itself is it's clear how to establish such a relation. But when we have some other set which contains some different elements, what do we do in that case, right? That's but I think we didn't find a specific. So we saw a reply. I think we asked ChatGPT or something like that whether it is possible, and the answer was yes. But I don't think we got a specific example of how it is possible, right?
mhm. So, like maybe like I'm asking to Tom here, have you encountered such situation in your studies because we didn't reach like that phase yet? So have you
Uh,
ever?
yeah, it's more of a like non-homogeneous Cartesian product can actually form an equivalent solution, but it's not always guaranteed.
Hmm.
When you are taking the homogeneous Cartesian product, I mean, it's guaranteed that it's possible to get a equivalent solution, but for the non-homogeneous case, it's not guaranteed.
Is there some simple example where we take non-homogeneous case? Can we take like two simple sets which are different and still create such a relation and just see how it is done, or is it not easy to do?
Hello?
Yeah, so it has
My connection.
about it.
I mean, like, if we have like I can imagine like if we have set A and like subset of A, I mean it is still different set, but we can get a like equivalence relation because we can make a reflexivity and symmetry with those. But if we have like ABC in one set and 1, 2, 3 in the other set, then we can't have a reflexivity, right?
Yeah, we cannot have reflexivity here, so that's
In
the
the
ultimate problem.
So the only possible case is like one set is subset of the other set, so that we could construct a reflexivity, or even not that case.
We'll in that case we can still lose the reflexivity, I guess, because elements from the bigger set.
Hmm.
Uh, how do we know elements from the bigger set which are not in the subset? Actually, we can get a reflexive like relation.
I mean, if we just construct,
Oh, okay, maybe it's possible. Yeah,
Mhm.
it's possible. It's
If
just
we just construct with like um
yeah,
based
it's
on a
possible.
small set, we can construct a
Yeah,
equivalence.
yeah, yeah.
Yeah,
It's
yeah.
possible actually. Yeah, but I think for the non-homogeneous case, equivalence relation. I you see, I'm not sure. Did Professor
Mm.
Cho said actually it is
Yeah, yeah.
possible to define?
I mean, it's not a main like interest for us, but we were just curious about the possibility. But I think we just found one possibility that like one one set is subset of the other set and different size. Two sets has different size. Then we call that different sets, but we can construct equivalence classes. I think we can back to our
I
exercise.
mean,
Our
maybe in simple way when you said it was set with 1, 2, 3 and ABC.
Mm-hmm.
I was thinking if you just generally give it consideration in terms of, let's say we say if the index of a letter in an English alphabet corresponds to the like the index value itself, then they're equivalent. So 1 would be equivalent to A, 2 would be equivalent to B, for example. It sounds like it's okay to relate it in the computer science sense of the way, like you can relate the first letter of the alphabet with the value itself, so A and 1 would be equivalent, but it's not very clear how you would formally specify such a criterion or such a relation, how you can write it out in a
I
sense.
mean, like in this case, the term equivalence you using here is like in mathematical sense, it means more like bijective function, but not mathematical equivalence relation. I mean, equivalence relation means like we have a exact same element as a pair to fulfill reflectivity, isn't it?
Yeah, this I think is a slight confusion in a sense. When you say exactly the same, it sounds like it's identical to itself, right?
Hmm.
So only one is identical to itself, but one cannot be identical to letter A.
Hmm.
But in some way, I think again in computer science you have the concept of separation. You have an address at which something is located,
Hmm.
and you have the same value but located at different addresses, and then you can sort of decide which one you want. Whereas in mathematics, I think this concept of identity or equality or equivalence is somehow more difficult to distinguish.
Mm.
I think it's even when we consider the case of modular arithmetic, we can say, for example, for modulo 3, 0 and three itself are equivalent, right? But they're not essentially equivalent in terms of how you write the values, but 0 and 3 are equivalent with respect to the value that they represent.
Yeah. So I think for time here, it was here, right? The like modulus of 3. So we can make equivalent classes for these. And
So they are essentially the same. I mean, not even different, right?
mhm.
Yeah.
So
I
like
mean, does it really matter if we talk about them explicitly because zero is class of zero equal to class of three, so just you just have to write something all the way to zero three.
so like Philip's question is we can make a we can call that like in this case 0, 3, 6, 9. These numbers are equivalents in mathematical sense, but why we can't say that like in computer science, like indexing sort of like A and 1, alpha and 1, like beta and 2, and why we can't call that equivalence in that sense. Is that your question, right?
That's at least it sounds like we are trying to say uh, the idea of saying if something is equivalent is about some kind of decision making. It is or it isn't equivalent, but
Mm.
this decision itself is based on some kind of uh, I don't think mathematics itself decides precisely whether you can agree on its equivalence or not. So with the modular 3 example, it's sort of mathematically precise, but with the example of number 1 and letter A, mathematically it's maybe ambiguous. So if you ask uh, one person whether 1 and A can be considered equivalent, he would say no. If you ask another one, he can say yes. But at the same time, it depends if you agreed that the criteria by which you decide is the whether it's an index in the alphabet or the index of a specific letter, and they can correspond. They can correspond. So if you
Yeah,
know
so
the decision
in that
criterion.
yeah, so in that case it's just like acts like a function. Like when we are talking about correspondence, we are just talking about the function or relation correctly. So then what matters most now is whether these two sets, like the sets of ones or twos and AB sets, whether they are the same. So are we labeling them differently or they actually are different but we have a correspondence? That's what we are concerned about, right? For example, when we are taking the let's say Cartesian product of x and y, so it's not there are correspondence between elements here too, but not necessarily they are the same. It's not like just a relabeling of it, right?
Mm-hmm.
So in that case, it belongs to the same problem as trying to define the equivalence relation of express, right? I mean, that's what I meant. I'm not sure whether it's clear enough. So it's more of like when we try to define the equivalence to x cross y. So we encountered some problem, for example, that's a property. It's not always there. So it is always only possible when one is a subset of another. In that case, we can define the equivalence. But in your case, we could take like one A, B, and C. So we are basically dealing with x cross y again.
I'm sorry, Philip, could you mute your mic when you are not speaking? I think there's some noise because of the yeah, yeah. And I think it's better for communicating. I think there's from noise coming inside of your mic when you are only not speaking. So I think you can, yeah. So and when you speak, you can just yeah unmute your mic.
We'll do that. Mhm.
Mm-hmm. And yeah, I think because we trying to as Philip pointed out, we trying to group some things have, whether in mathematical sense, equivalence, or so we want to group different things together, have certain aspects. As Philip said, like alpha and one, like these indexing numbers, we can also group them because they have some aspect. But we can rather say that equivalence, we can say we can express that in bijective mapping in mathematical sense. So somehow in mathematics we trying to distinguish those like strict equivalence, which represented by equivalence relation, and bijective mapping, which also plays a important role in mathematics, I guess, but we don't say that as.
Maybe I'm just asking, is it possible to just take, as long as you have a bijective mapping between two sets, it doesn't matter with which elements, but as long as you have a bijective mapping between them, and you say it is a criteria by which you decide if they're equivalent or not, it is sufficient to create an equivalence relation. So as long as precise rules which are mapped one-to-one exactly, so like one-to-one and onto, so bijective, then essentially you can equate any two things in a precise way.
Yeah, but we are not guaranteed to get reflexivity, so it is not sufficient, in my opinion.
Yeah, it's not sufficient from my opinion too, because we don't get
Mhm.
reflexivity actually. Even I think in some sense we might not get even symmetry also.
Mhm. Yeah, I mean, if as you said, like alpha one, like set of one, two, three, and set of alpha, beta, gamma, and if you have a bijective mapping to alpha to one, beta to two, and gamma to three, then we don't have reflectivity and even symmetry or trans. I mean, yeah, not symmetry at least.
But my question again, so we don't get reflectivity from this bijective connection, but why can we not have reflexivity, like one is related to one as well?
No,
A is
I mean
why
we
not?
have alpha to one, but you mean like mapping like here? Sorry, I don't have a pen today, so I will use my
Okay,
hand. So
we
here
use
we have alpha, beta, gamma, and here we have one, two, three. So mapping is alpha to one, and beta to th two, and gamma to three.
So well, my question is that I agree that it is not sufficient, that it's not sufficient to just have this mapping, to just have this bijective mapping. But as long as we have it, this is how we can connect two sets with very different elements. So as long as we can still, I think, have outside of this bijective relation, outside of this bijective connection, we have reflexivity, because we can still say one is equivalent to one. So one is reflexively related to one.
How can we
But
say that?
uh, basically, yeah. So I'm just saying that we use this bijectivity of two different bijective connection between two different sets only to be able to figure out if two elements from different sets are related. But to decide if elements from the same set are related, then we don't need this sort of
So
mapping.
I think for in terms of communication, I think you should specify which two sets you are doing making a Cartesian product. So in your setting, which two sets you are doing Cartesian product and get the relation from there.
But then maybe the question goes. Then if we have a Cartesian product of sets which separately are not containing the same elements, then how can we have an equivalence relation at all? So how can we at all have an equivalence relation when we have different sets, so non-homogeneous case.
I mean, if you have like one, two, three
Mhm.
as set A and one, two to set B, so these are different sets.
But the one is the subset of the other. So
Yeah, yeah.
it was the case you were talking about before.
Yeah, yeah.
Is it possible to have an equivalence connection when they're actually different? So when they're not, one is not the subset of another one.
Like,
No, I don't think it's possible.
yeah, also like in my opinion, we can't because we can't get a reflexivity.
Mhm. So maybe that's why I'm asking it is to clarify. So maybe when the professor mentioned that it's possible to have non-homogeneous case, what he meant was that it's non-homogeneous in the sense that one set is smaller than the other, but it is actually a subset.
I mean, that is one possibility. I don't know whether there are other possibility, but I think that could be one possibility. But at least if we don't have a reflexivity, that does not fulfill the definition of equivalence relation. So I think we
Mhm.
can't.
No, I'm just actually trying to find this kind of example where it's possible to have non-subset relation between two sets, such that it's still possible to do it, but I cannot see it. Yeah.
Mhm.
So I think the example with the subsets that you mentioned makes sense, but I don't see any other examples that would also
Yeah,
work.
yeah, me neither actually. I don't think actually it's possible other than something else.
Mm.
Because like there's no more like implicit in the reflexivity. It's just like it should be X related to X, then we can't get reflexivity. So yeah. So I think we didn't finish the second one, like from partition to equivalence relation, right? Yet. So this is the end of our note, but I think we should go through the this part and then finish our meeting today. So we still pending on our second direction. So reflexivity, we can get a reflexivity because we have a Cartesian product and xy is from the same subset, then we have a reflexivity. So
Yeah, because we can just write x comma x is element of the alpha.
mm-hmm. So I think it's a bit trivial and so I think it's a bit obvious and what's so how could we show that symmetry?
I think we just change the order. I mean, x comma y is element of ex is the same as y comma x is element of e alpha, sorry. So x comma y is element of e alpha means the same as y comma x is element of e alpha. Okay, maybe it needs a
Ah.
little bit clarification. Wait.
I'm
Mm.
for myself. I'm wondering. So let's say we pick two elements from E alpha. Then can you find an example where it's x is related to y, but y is not related to x? If both of them essentially come from E alpha, that's not possible, right?
Yeah, that should not be possible actually. Because if x is related to y, which means x and y is element of E alpha, then
Mm.
obviously we have y comma x is the element of E alpha, so y is related to x.
Yeah, I was a bit confused because x comma y I thought that as like pairs, but it actually means like x is from E alpha and y is also from E alpha. So
Yeah,
right?
yeah.
Yeah, yeah.
The
So
pair exists inside the E alpha,
mhm,
not
mhm, mhm, mhm.
So just on the technical side, I think my connection sometimes gets disrupted. So I hear you maybe after like 5 seconds or something like that. So if it's slow, sorry for that. Yeah.
So we have X and Y in E alpha, right? And since we have a Cartesian product, mm, so we have Cartesian products like X Cartesian product X, like large X Cartesian product large X, and E alpha is subset of large X. And our setting is X and Y is inside of the subset E alpha. Mm-hmm.
Isn't it the same like we are trying to show that X is related to Y? Initially, sorry, not we are not trying to show that. So initially we have X is related to Y. That's how X and Y are element of E alpha, right?
You mean we already have the
Yeah, X is related to Y already. We are just trying to prove the symmetry case. I mean,
To me, what it sounds like is that it's a bit difficult to sort of see the causality, which one is the beginning and which one is the end, essentially. But when we say we take a class E alpha, it means that the elements inside E alpha are all equivalent in the first place. So it's kind of it's kind of but then what you're trying to show is that show it is an equivalence relation, show it satisfies the properties. But then if it contains elements which are equivalent, then how it's more like how can you not have the properties which would satisfy the equivalence relation to me, which makes it a bit confusing.
yeah, so we are in the symmetry case right now, right?
Yeah,
Mhm.
yeah.
Yeah, so by default, we have X is related to Y and XY is the element of E alpha, right?
Mhm.
I mean, for the symmetry case, we don't have to think about the existence of the case that whether X is related to Y. We have to
Mhm.
start from X is related to Y. Yeah, so if X is related to Y and such that XY is element of E alpha, and then we can say that let's say in terms of instead of XY, we can say that YX is also element of E alpha. And by that we have Y is related to X because it's the definition.
I mean, um,
I mean, I'm just saying we are just changing instead of saying XY is element of E alpha, we are saying YX is element of E alpha because it's basically the same. And when we are saying that, we are creating that Y is related to X.
mhm. Mhm.
So
So,
yeah, we're still considering the case of symmetry property, right?
yeah.
Yeah.
Mhm.
Mm. Yeah, yeah, I get it. So, like this three line is just how we define this relation. So if we just exchange the the like place of X and Y, we just get like Y and X, like Y comma X in X and Y comma X in E alpha, you mean? That's
Yeah,
what you
yeah,
mean.
yeah, yeah.
Ah, yeah,
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 yeah, yeah.
yeah, yeah. Okay, okay. Now I got it. I mean, is it clear to you, Philip, too?
It seems so, but I think basically if we go now to transitivity, maybe temporarily, then we can return if we need to. But I think for transitivity, we can say the following. If X and Y are both belong to some E alpha, then we can say that X is related to every single other element in E alpha, which means that there is no possibility to not have a transitive relation. So I'm wondering if that also makes sense.
I couldn't hear the last line properly. What did you say?
So we say both x and y come from some E alpha. If
Yeah.
both come from some E alpha, then we know that x would be related to every other element in E alpha. Because it is related to every other element in E alpha, we automatically get transitivity property. If it was not related to every element in E alpha, maybe it's possible to miss some element in the transitivity itself. But because it's related to every other element, then it's impossible sort of to not have transitivity from how I see it.
Yeah, actually.
But I'm not sure it makes sense.
Yeah, this is from the definition of I mean this comes from the definition of the classes. Yeah. But maybe we can maybe try to say, let's say we have x is related to y and y is related to z, and then we have to show that x is related to z, right? I mean,
Yep.
that's the question. Yeah.
Yeah, would be
So
the
now let's assume that x is related to y and they belong to E alpha. And then let's say we have y is related to z and it belong to, let's say, E beta for the sake of conversation. But then y belong to two classes now. But this is technically not possible because the intersection of two classes has to be non-empty, so it has to be empty. So by default, then z belongs to the same classes as x belongs to. So by default, they have a relation, or x is related to z. So that's how we use it. So that's what Philip said actually, but he also used the definition part of the class, like by default as x is related to y or x is related to z, they belong to the same class, so there must be that x is related to z.
Mm-hmm.
And I think it's actually nice that you also considered the non-intersection of E alpha and some E like with a different index.
Yeah.
Mm-hmm.
Yeah, so transitivity is also xy and yz. Then we know that xyz is element of E alpha. So we can just pick xz as a pair of E alpha, then fulfills this criteria.
Yeah. So that's the by definition case.
Mm-hmm.
By definition, they belong to the same class, so by definition, they have an equivalence relation, or they have a relation. But at the same time, even if someone wants to be a little bit formal, they say that XY belongs to a class, YZ belongs to a different class. But then we have a contradiction that the intersection of two classes is basically Y, which cannot happen. So they must belong to the same class XYZ. So that's how we get X is equal to Z.
Mm-hmm.
How I see it, I think this concept of non-intersection is necessary component in the proof, right? So like if we had to formally write it out, if we missed specifying that two different equivalence classes cannot intersect, then it would not be sufficient. So we have to say that it's necessary.
Yeah.
Mm-hmm.
Makes sense.
Mm-hmm.
So for the transitivity property, the fact that turbulence classes, sorry, not classes, the classes are disjoints, partition blocks are disjoint. This property is actually important. I mean, in the proof step to show.
Mm-hmm.
Like, where like in the reflexivity, we had a different issue, right? For the reflexivity, what did you get? I forgot.
Mm-hmm. Okay, I think we can conclude our note then. So we have a correspondence, one-to-one correspondence, maybe even bijective mapping.
Okay, so equivalence relations on X is partition. Oh, okay. Do we have to prove this?
No, no, no. I think we get this from previous two,
Oh
thankfully.
yeah, yeah, yeah.
Yeah. And so precisely the equivalence relations are same as the set of the equivalence classes of X. So how can we formally describe this in formal sentence? Um, so if you have a equivalence relation, we can form a partition by the set of equivalence classes. And if you have a partition, um, like the way we did here, we can get the relation as a
Yeah, so we have a partition. Every partition induces an equivalence relation.
mhm, yeah.
Just wondering, can you casually say if you can split a set in an unambiguous way into groups, then essentially each group would represent an equivalence relation between the elements of that group.
Each group.
So you take just some random set, you split it up, and the groups which form by this splitting up end up being equivalence relations.
Equivalent classes, like each subset will be equivalence classes.
Uh, yeah, yeah. Essentially, each division of would be an equivalence. So in other words, you take a circle, you cut it in half.
Mhm.
One half would be elements equivalent between themselves, and the other half would be elements equivalent to themselves.
Mhm. Yeah.
Because I'm just in the case, if it's you do not split the circle at all, then you can say the set contains every element is equivalent to itself. So a set that cannot be split in any way, every element can be related to itself. It's one case, and the other edge case would be if you split a set in such a way that no elements are related to each other at all. So every element is sort of unique, but then it's still it still can show, yeah, basically. So in this set, every element is not equivalent to every other element.
Mhm. Yeah. So I hope I
I
think
think
mhm.
in our study we had this two edge cases essentially. One when there are no divisions at all, and the other one where everything is so granularly divided that every single element is different, right? So I
Mhm.
think. But then
In
my
that
question.
case, maybe, yeah, in that case, every single element are uniquely defined. So in that case, we have singleton classes. I mean, the only element of this class is the element itself. Like we have class of one, basically the element one.
We have only the reflexivity essentially property, but and because it only contains one element, the reflexivity is sufficient. So we
Yeah,
don't
exactly.
need
Yeah, yeah,
transitivity and
yeah,
symmetry. Yeah.
exactly.
Yeah, so I think I should wrap up this meeting now. So we finished the set theory part. So I hope we do the exercise just ourselves and maybe try to write down formally at least once. It's not mandatory, but if you try it, just share your solution to our channel. And then, as I told you, there's the calculus problem set, ABC. So I hope we also take a look at this and just go through these ones. Maybe it will be more like review what we learned in what we did in high school. And then also I hope we can go through the real introduction to real analysis. So we're beginning of new chapter. And if we have some questions and if you want to get some feedback, we can always have a chance to do a meeting with Professor Cho and get some feedback. But um, I I have to excuse me because I'm in vacation, so maybe after like 3 weeks, I hope we can do a um like feedback session with Professor Cho. Or if you want, we can do that, but yeah, maybe I could not be there with you. But yeah, so this is it for today. And any comments and questions or suggestions?
I think I have only one sort of material organization question. When you say, for example, today we covered Note 3,
Mhm.
but you say Note 3, where do you take this number from? Like Note 1, Note 2, Note 3? Uh,
So you can check the like PDF. There was like 1 to 120 notes,
yes.
and mhm. And
And
in the Google
where
Drive it has like numbers of notes. But I think not inside of the notes it has a number. But also the lectures, like videos, has the number from Professor Cho and also the materials from our Discord channel. So I will just forward the link to you again.
thank you. Yep, I think that's it. Yep, thank you.
And also from your side, Tamfir,
No, I don't have any question.
yeah. Then I think I can finish the record now and yeah, have a nice day, have a nice week and see you
Yeah,
next
have a good
Monday.
week. You are on vacation, so
Yeah,
enjoy
thank you.
yourself, I suppose.
Yeah, and have a nice day to everyone as well. Thank you.
Yeah, okay, thank you. Have a nice day.